So we have carbon dioxide entering a well-insulated diffuser operating at steady state at a pressure of 70 kPa and a temperature of 290 Kelvin with a velocity of 195 meters per second. The inlet area to the diffuser is 50 centimeters squared. The diffuser exit, or at the diffuser exit, the pressure is lower, no, it's higher because it came in at 70, it comes out at 90 kPa, and it's slower at the velocity of 65 where it came in at 195. Okay, the gas behaves as an ideal gas with this value of K, and when you see that, you will go ahead and just stick with constant specific heats. So if I'm looking at CO2 as the gas and this value of K, then I expect if this value of K was picked correctly, it was picked at an average temperature between the inlet T1 and the exit T2. Just take the average as a good enough approximation to get an average K. And then if you needed C sub P, back in chapter 3 when we studied ideal gases and introduced specific heats, we had K times R divided by K minus 1. So you get the gas constant R for carbon dioxide and then use that value of K to get C sub P. Likewise, C sub V is simply R over K minus 1. So when you see this, this is the wording. Basically, it says don't use the table for temperature-dependent properties for CO2. Just use constant specific heats, and this is the way you can get them, right here and right here. Okay. Then we ask, or the question is for part A, what is the exit temperature in Kelvin? Now notice, if we do calculate that it would be 310, if it came in at 290, what is the average temperature? Well, 290, 310, add them together, divide by 2, it's 300 Kelvin. So let's still do a quick check. We can take a look at table A22. It'll have carbon dioxide in it. We come down and we find 300 Kelvin, and K is 1.288. So what was the value given in the problem? 1.288. And so that makes sense. And if you want, you can compare this value of C sub P in the table and that value of C sub V in the table with the equations. And they're not perfect, but they're good to 3 and sometimes 4 significant digits. So let's press forward on that. So how do we calculate this exit temperature? Then we'll calculate the exit area and then the rate of entropy production. So make a sketch. What is a diffuser? It's an increasing cross-sectional area, and what it's going to do is you have pressure recovery where the exit pressure is typically greater than the inlet pressure if it's a good diffuser, and it slows it down so the velocity at 2 is less than the inlet velocity. So it slows it down and recovers some of the pressure. Okay, now we're going to introduce a control volume right here, and we'll do 3 types of balances. We'll do a mass balance, energy balance, and entropy balance. Now the entropy won't come until part C, but for the mass flow rate, well, mass flow rate in mass is equal to mass flow out. There's just one mass flow rate through the system. We take a look at what information's given. They give us this area, cross-sectional area coming in at 1, the velocity at 195 meters per second. This was 50 centimeters squared. Inlet pressure of 70 kPa, and I forgot to put the inlet temperature of 290 Kelvin. Well, you take a look at this, and you've done it a few times, but can you get the specific volume inlet flow? Sure, that's going to be the RT1 divided by P1, where I'm going to put R over here. R is the R bar divided by the molar mass of our gas. The gas constant, or the gas is carbon dioxide. So this is 8.314 divided by 44.01. We got the molar mass for carbon dioxide out of one of the tables, table A1 in our textbook. So we have the value of R. So we have the value of R, T1, P1. You can compute that the specific volume coming in is 1.2297 meter cubed per kilogram. Okay, so we know the specific volume. We know the volumetric flow rate because it's the product of the area times the velocity. So that's our volumetric flow rate. Here I'm going to do it a little slowly. So our area is 50 centimeters squared. And so it's like centimeter times centimeter if you want to do it slow. And then you just say, well, 100 centimeters is a meter, and another 100 centimeters is a meter. So we cancel. I know I'm doing this ridiculously slow, but I found that this is error prone. So this turns out to be 50 times 10 to the minus 4 meters squared. That's a 50 centimeters squared is 50 times 10 to the minus 4 meters squared. Okay, that's our area. Then we multiply that. I should have just left that alone for a minute. Just say this is the area 1. Now area 1 times velocity 1 will give us the, we have the area, we have the velocity, the volumetric flow rate, 0.9750 meter cubed per second. Okay. And now if we want the mass flow rate, m dot, you take the volumetric flow rate, AV, and you divide by the specific volume 1, because that's the volumetric flow rate coming in at state 1 divided by the specific volume at state 1. We have the specific volume, we have the volumetric flow rate, the mass flow rate comes in at 0.79288 kilograms per second. And again, we're keeping all these digits in our calculator. We don't want to round off and then continue to make round off errors. Okay, now we have the mass flow rate. We know that mass flow rate in is equal to mass flow rate out. We're done with the mass balance. How about the energy balance? Well, when you do the energy balance, you have the inlet enthalpy plus the inlet kinetic energy is equal to the exit enthalpy plus the exit kinetic energy. And we're going to be using constant specific heats. So let's rearrange it. We'll put H2 minus H1 is equal to KE1 minus KE2 if we didn't do any algebra errors. That looks good. Then we'll use the specific heat. T2 minus T1, KE1 minus KE2, and now I can solve for the final temperature. Exit temperature is equal to the inlet temperature plus KE1 minus KE2 divided by the specific heat constant pressure of our gas. Okay, so do we know T1? Yeah, it's right here, 290 Kelvin. How about the kinetic energy coming in? Well, the specific kinetic energy coming in is 1/2 velocity 1 squared. I'm going to go slow here because this unit conversion, a lot of people will miss it. We put in our velocity, 195 meters per second. We're going to square that, divide by 2, but we do a unit conversion that 1,000 meters squared per second squared is 1 kilojoule per kilogram. So after you do this a few times, basically it's like just take the V squared in meters per second and divide by 2,000 instead of 1,000, and then you'll get it in kilojoules per kilogram. But that's why, because of the unit conversion. Okay, so we pick up that this is 19.0125 kilojoules per kilogram. And the specific kinetic energy at 2 when the velocity at 2, I should have written it down up here. Let me go ahead and add it. So we're given the pressure at 2 is 90 kPa. And we're given the velocity at 2 is 65 meters per second. We calculate the specific kinetic energy at 2 is 2.1125 kilojoules per kilogram. So we have both specific kinetic energies, and we have the inlet temperature. We need that C sub P. Well, here's our equation right here for the specific heat. We already know our gas constant. I didn't write it down, but gas constant is R bar divided by molar mass. And so 8.314 divided by 44.01 equal to, and our gas constant comes in 0.18891 kilojoules per kilogram Kelvin for CO2. And then we calculate C sub P, and I'll just try and write it in here. And we find C sub P is 0.8449 kilojoules per kilogram Kelvin. Didn't leave enough room. Sorry about that. We don't need C sub B. We could calculate it, but we really don't need it. So now we have the C sub P value right here. Run your numbers right now, and then you can solve for T2. And T2 will come in at 310 Kelvin. Okay. Now, that's part A. What about part B? Well, you use the energy balance and you use the mass flow rate relationship coming in. Basically, the mass flow rate on the exit and the volumetric flow rate, etc., on the exit will determine the exit area. So let's go ahead and write that out. So the mass flow rate at the exit is equal to the volumetric flow rate at the exit, A2 V2 divided by the specific volume at 2. In this equation, we're looking for that exit area. So I need to scoot down. I hate to do that, but I can't fit it all on one page. So what we find is that area 2 is equal to our known mass flow rate, which is same as mass flow rate in, mass flow rate out, times the specific volume at 2, divided by the velocity at 2. And so I'm going to put it right here. Area 2 is equal to our mass flow rate. We have it right here, 0.79288 kilograms per second. And then we have our specific volume at 2. The same way that you solve for the specific volume at 1. Specific volume at 2 is equal to that R, T2 divided by P2. And this comes in at 1.0224. What are the units? Meter cubed per kilogram. So we'll just put it in right here, 1.0224 meter cubed per kilogram. And then we divide by our velocity at 2, which was 65 meters per second. So just you do the units to double check everything. Per second goes, and you're left with meters squared. This area comes in at 0.01247 meters squared. So the area 2 in centimeters squared, you just move it over 1, 2, 3, 4. So it comes in at 124.7 centimeters squared. And that's our answer for part B. Okay, last part. What's that rate of entropy production in the diffuser? Well, for the same control volume right up here, we want to write our entropy balance, and I do need to scoot down, I'm sorry. And so we have the entropy balance and we have our rate of entropy production is equal to the mass flow rate times the exit entropy minus the inlet entropy. There's a few steps if you start with the most general equation, but this is the final. You need to get to this form, and it's just 2 steps in algebra. And we look at it, we say, well, we know the mass flow rate. We need to calculate the change in the entropy. There's 2 ways of doing it: constant specific heats or variable specific heats. We're going to use the constant specific heat. So S2 minus S1 is equal to C sub P, natural log of T2 over T1 minus R natural log of P2 over P1. And guess what? We know every one of these. We know the inlet temperature, the exit temperature. We know the specific heat constant pressure. We know the gas constant for CO2, the exit pressure, the inlet pressure. Boom. And you can calculate the change in the entropy is a positive 0.0088777, way too many digits, but kilojoules per kilogram Kelvin. Multiply that by mass flow rate, we get the rate of entropy production to be 0.0070 units kilowatt per Kelvin. That's our final answer for part C. Well, I hope you found that helpful. Thank you very much.